Hello, everyone. Good afternoon. Thank you so much for making it here. We're really excited to share the product of our work for the better part of the last year. We're Group 10, supervised by Dr. Hossam Sharara. With me here, joining me on stage is Yousef Eid, Ahmed Wael, Nourhan Nada, Adham Hegazy, and Bassel Akrum. So we'll be going to a lot of content right now. We're starting from the problem statement all over to the power empowerment outcome. We're making sure that we've actually created our commercial product. And so let's start with the product statement. What is the problem that we're trying to solve? Even though we have a lot of advances in facial recognition technology, we're seeing a gap between what's there in the research and what's there in the final product. Right now, facial recognition technology in a security environment is usually a really bulky system that is not flexible and not with a lot of space for maneuverability and other stuff. And so we've set out to change that. We have a lot of different problems with the current set of systems that are available. There are high maintenance costs. There is a really costly infrastructure and a lot of associated overhead with that. We have a lack of flexibility with the product itself. So the products are not portable, they're not maneuverable. You cannot change that through the agent, and they have limited coverage. So they're usually indoor products. You cannot use them in an outdoor environment. And so we set out to create a product that is mobile. So it needs to be portable. It needs to be movable by the agent with a lot of maneuverability. It needs to work in real time, whether in an environment that has an online connection or an offline environment. And it needs to be accurate and reliable. Without further ado, we would like to present our product, Hexavision. So Hexavision is a portable device that could be worn by the operator. It could be attached as a clip or worn as shown here. We also have two different companion apps. So we have a companion app for mobile phones that could be used by the security agent to make sure they're getting real-time identifications. And we also have a dashboard where the central admin could actually insert newer identifications or identities. So for a bit of a system architecture, we have three main components. As we've mentioned, we have the edge device itself, which is a Raspberry Pi for Turbo. We have a companion app that is built on React Native, and we have a dashboard that's built on Flask. The dashboard itself is connected to a Postgres database that has pgvector enabled to enable for quick access and searches for the embeddings. And we also have a local cache to make sure that the mobile system could actually work in a completely offline environment.
All right. I'll be giving you an outline of our peripheral specifications. All right. We have two main components, the first being the Raspberry Pi 4 and the other being the Raspberry Pi camera module V2. The Raspberry Pi 4 comes with a built-in 32 GB micro SD card, a 4 GB RAM. It's powered by a USB-C supply, USB-C. It has a micro HDMI to connect to an external monitor, and it also has a built-in Wi-Fi and Bluetooth. As for the Raspberry Pi camera, it has an 8 megapixel resolution and a 1080p video. All right, in terms of the peripheral integration, we have an external monitor where we can view the camera from. We also have the Raspberry Pi where we connect the Raspberry Pi to the external monitor through the HDMI port. We have the Raspberry Pi camera module as well, a Wi-Fi connection to send and fetch the APIs from the server, as well as an audio connection to get the feedback if an identity has been detected. Now, as for the pipeline, I'm going to be giving you a brief or a basic flow of our recognition pipeline. As you can see from the flowchart, we have Messi entering the building, and we have our security personnel with our product Hexavision. It's going to detect his face, and it's going to send his embeddings to the local memory. If an embedding is found in the local memory, then it's going to just say, great, the Messi has been detected, and it's going to add to the visit table. However, if the embedding is not found, it's going to search, it's going to send the embedding to the central database and search for the embeddings over there. Now, if no embeddings are found in the central database, that means that Messi is not in the database and he needs to be added. However, if he is found, then the embeddings will be sent back to the Raspberry Pi and then added to the visit table. Now I'm going to be passing on to Adham, who's going to be talking about the back end and the database.
Okay, so with the backend, as the pipeline described by Yousef, we have a lot of communication happening between the backend and the mobile device and the Pi. So that's why we needed to make this process streamlined and as efficient as possible. So we started by, we developed the backend using Flask, and we hosted it on Python Anywhere. So the main task or the main functionality of the backend was basically to handle the communication between all the endpoints, all the devices in the pipeline, started from the central database to both the Pi and the mobile app. So it handles the API connection that is utilized by the Pi and the app to retrieve and take the data, as well as connects with the central database and take from it the embeddings, along with comparing these embeddings in order to find a match. And if the Pi has a visit, then of course it takes the visit and registers it into the backend to the database. However, there is a huge amount of computational power used for just to generate the embeddings and store them in the database. So we didn't want that to hinder the communication of the APIs. So that's why we used a background process, which is always running to generate the embeddings for new images being registered in the system at the backend. Then again, you can imagine that there's a lot of flow or volume of data going in and from the database. So that's why we needed to design it in the most efficient way possible. We used PostgreSQL and hosted it on a Supervised server. This stack allows us to use a PG vector, which is one of the most efficient ways to store and search for the embeddings. As basically, this is the heaviest amount of data transaction is in the database, so that's why we prioritize this stack, along with also using inverted indices, which allows us to be really scalable with a huge amount of faces on the server. And now Wael will talk to you through. So again, like the Pi, we're dealing with a really limited device. With a limited storage. So it kind of reminds us with the RAM. It's really limited storage that we need to utilize in an efficient way. So naturally it comes with a lot of replacement. What determines which to replace is the caching policy. So first we limited the stored faces on the Pi to a certain threshold. And if the identity was not found locally on the database as described by Eid, it will be found, it will be fetched from the central database. So once we fetch the closest match, what determines actually which identity will be replaced in the limited identities on the Pi is the caching policy, which we decided on to be the LRU, which is the least recently used. So basically, the least person who accesses the campus, the least data who access the campus will be replaced with our newest fetch. So that's kind of a natural way for the use case of the campus. Again, if it's another use case, it would be similar form. That's why the LRU we decided on it. Yeah. Now, actually, I will go with the model.
Okay, so the next part in our presentation is the machine learning model. But before we go into the details of it, I would like to take a step back and just introduce to the audience what an embedding is, seeing as we might have been using the term very loosely without establishing what an embedding is. An embedding is a representation of the face, which allows us to match the face of a person to their face again, even if they're wearing different things, they are in different lighting, they're indoors instead of outdoors, etc. So the machine learning model is built on 4 steps. First, there is the face detection, which from the video live stream that is detected by the camera on the Raspberry Pi, we are able to identify that there exists a face. There is someone passing by, they possess a face, we know that face. We detect all of the faces in a frame, maybe 2 or 3 friends are walking together and you would notice all of their faces. The camera would detect all of them, and then it would bound their faces with a box or surround it with a box. All of those faces are then resized. We resize them in order to increase the processing and to make sure that the data that is going into the 3rd stage is compatible with its requirements. The 3rd stage is the embedding that we have been talking about. It is essentially a representation of that face as a vector of numbers, 128 numbers to be specific. And we generate that by passing the image through a convolutional neural network, a CNN, to generate that embedding. And finally, as we have been going on for quite a while, we match those embeddings to either those found in the local database or the remote database, as we have established. We tested two different machine learning models and compared the results that we obtained from each and decided on the best fit. So we used dlib and FaceNet. dlib is directly implemented in C, which is a very famous programming language, and FaceNet is implemented on Keras, and which we have then implemented in TensorFlow Lite. Due to the difference in implementation, dlib performed better both in computational performance. It was faster and it generated the data much quicker, and it was also more accurate compared to FaceNet, which had worse performance. We made sure to use the same pre-processing on the Raspberry Pi as on the back end to make sure that the embeddings match, so that we do not have an embedding that is 128 numbers in size and another that is 1,000. Those would be incompatible. We need to make sure that they're the same embeddings and generated through the same way. The model pipeline is, as we have established, we detect a face, we generate the embedding, and then we compare to the local database that exists on the Raspberry Pi. If we find that face locally, we add it to the record of visits that we have, and we identify this person. If we do not find it locally, instead, we go through the longer pipeline of sending that embedding, the live generated embedding, to the backend. It compares it with the embeddings in the database. It returns the best fit. If that best fit is within a certain threshold, we accept it, and then we do the same by adding it to the visitor log and identifying the person. Next, we will be talking about the admin dashboard. However, we have an entire demo dedicated to it, so I will be just going over that section very, very briefly. The main features that we have on the admin dashboard are adding a new identity, a new face or a new person, and adding a new event. We can also view the old identities and the old events. These are some of the screenshots of the admin dashboard. Here, for example, top right, we can see adding an identity. Bottom right, we can see adding an event. Bottom left, we can see the identities that we have, but we will show you those in greater detail in the demo. These are other screenshots, which are quite redundant.
Now, in order to enhance the overall experience, we've created a companion app that the user will use. So now it uses React and JavaScript, and we use a framework called Expo. And the reason we use these languages is because they make it cross-platform, which make them easily deployable on an Android or an iPhone. Now, the APIs we used are APIs we've created in the back end, one that retrieves user information and the history as shown in the screen, and others that retrieve the actual details of the identity identified. So the features of the app include viewing the history, as I previously said, and authenticating within real time. So this is an example of a user that is blacklisted, and that is another example of a user that's not blacklisted and is allowed entry. Now, with regards to the actual product that we previously talked about, it is encased in a 3D printed customized case that we've printed here on campus. It is also allows it to be wearable. There's also another use case where you can place it on a tripod for stationary use cases, say in front of a gate or so on. Now, there are two methods of feedback from the application, from the device. It's either visual, it can be connected to a monitor, or through the app, which shows you the currently identified user. Another way of identification is it gives you audio. So when a person is identified, it'll play a ding, and you'll see it in the demo. And if a person is blacklisted, it'll tell you threat detected. The person is not allowed access. So we'll just be taking you through the demo video.
So before we dive into the video, let's just give a quick context about the video. As we can see here, there are three different screens. The first one is the admin dashboard. The second is the mobile app. And third is the actual real-time detection. Let's assume for the sake of context that this is Amr Diab concert in this context. And all the feeds are in live view.
Okay, now log in. Okay, using live detection. ماشي. نور. نور.
As you can see, we hear the ding because Noor is already in the database and we matched her already. This person was not in the database, so nothing happened. So we're going to add his identity now. We will add him in this scenario as a blacklisted person to the event, so he will not have access. As you can see on the top left, the admin dashboard, his identity has been added.
Okay, so I think
Now we're going to scan him again.
Warning threats have been identified. Yousef Eid is blacklisted.
As you can
He's
see,
blacklisted as mentioned by the audio and by the feedback on the application.
listen, okay, so since we're a commercial product, we obviously need some kind of business plan or a business development. We're not going to go into detail, but we do have a business plan, and we're going to dive into the three main components. Our first part or component is the go-to-market. Which market are we selling this product at? Which is, upon research, we decided with the authentication and security market, in specific the facial recognition market. Upon further analysis, we found out that approximately 3.86 billion is the current market size or the market revenue, and it has as of now it has a compound annual growth rate of about 15.4%. So around by 2028, it's gonna be estimated around $12.11 billion, which is really good for our product, and we have future sales and future profit in this market. As for our consumers, here are just some examples of who we can sell or who can use our product. The first thing that comes to mind is any small to medium business who want to secure access control or to even verify the employees who attended today. Another consumer is any event management companies who have regularly host concerts or trade shows or any other large event. They can be used for anyone who is blacklisted from the event or any attendees check. And also because we have the blacklisted feature, we can also, this is very valid for any law enforcement and security agency, because anyone who's blacklisted, obviously the law enforcement can use this as a watch list. And also the healthcare providers can use this to track down patient and also for any employee attendees. And finally, our main use case, which is in the educational institutes, which is obviously, for example, in AUC campus, where AUC security can use it to scan all the students or even any intruders who don't belong in AUC. As for our final component, the pricing plan, we offer two main plans, the one-time fixed payment and the subscription fee. Our final cost of the one-time payment is $149, which is broken down into the base cost of the Pi camera, and the Pi case, with a 6% markup, as well as installation fee. The second, the subscription fee, we offer three main plans, which is the monthly, semi-annually, and yearly. And they all have a base of 8 GB database storage and 100 gigabyte file storage, as well as an enterprise plan. And this plan is made if you want anything extra, you can contact us directly and we can customize a plan for you.
Now, throughout the past year, we've been working towards our empowerment outcome. So we've created a commercial product that is a wearable device, achieves reliable results, has a user-friendly experience, and is aesthetically pleasing, if I do say so myself. Thank you very much. I'd just like to take a moment to thank our advisor, Dr. Hossam Sharara, and thank all the hard work of my thesis members and all our family and friends that have come here today and have supported us throughout the past year. Thank you.